Okay, welcome my Math 150 students. I'm trying something new. I'm trying to do an audio and a video explanation of all of these sections. So I'm beginning with 4.1. This is new to me. Just please be patient with me. So I'm going to begin. So before spring break, we spent a lot of times talking about linear functions. So kind of doing a recap. If you look at this chart, remember I've always stressed about patterns. So when I'm looking at this table, I want to know, what are my x doing and my y doing? Well, if I look at my x, it is going up by 1, and my y is going up by 2. So now, if you go into your L1 and L2, and we go to stats and then option number 4 for linear regression, I'll give you, if anytime through here, just pause and you can put this in your calculator. So if you look at this, I get A to be 2 and B to be 0. So this is linear because they're going up the same amount, 1 for the x and 2 for the y. So my overall function would be y of x equals, remember A is my, in this case, my m. So 2x, you can put a plus 0 in my opinion because that's telling you what the y-intercept is. Now, if you're looking at this chart, you can plug these values in. So I'm going to look at, if you want to look at, scroll all the way down to the 4 right here. If you put 4 into this equation, 2 times 4 is 8, plus 0, that gives you that y is 8. So this is a linear function. Now, I'm going to scroll down to the next set. I'll give you some time to look at this. But now in example number 2, the same scenario. Look for patterns. So if I go all the way down to my x value, going up by 1. Take a look at my y, it's going actually up by 3. So if I plug this in my calculators with the L1 and L2, your A in this case is going to be 3, and your B in this case, which is our initial value when x is 0, so y is 1, that's why B is 1. So as far as linear is concerned, your formula would be y of x equals, in this case, 3x plus 1. Now you can try all of these if you want to, but you take a look at the last one, x is 4. 4 times 3 is 12 plus 1, gives you that y is 13. So this kind of gives you a little review about this gives you a review on linear, what we talked about before. Now, can't get this. Sorry about this. There we go. Example number 3. I want you to think about for a second. So if you want to pause for about a minute to see the pattern, go right ahead right now. Okay, x. What does x do? Well, this case, x is going up by 1. But now take a look what our y is doing. It's multiplying by 2 or doubling it. Okay? So in this case, and we're going to learn this later on, but what our formula is going to be for any of our exponential is going to be a times b to the x, where A is my initial value and B is what my Y value is doing, whether it's doubling, tripling, cutting it in half. It's what it's doing exponentially. So just by this example, when X is 0, that's our initial. It's going to be A is 1, but B is, we're doubling it, so that's going to be 2 to the X power. This is exponentially what it should look like. Now, as far as the A is 1, you don't really necessarily have to put that, but I'm just showing you that 1 is because that's showing us what we're initially starting with. Same thing with problem number 4. So I want you to pause for a few minutes. Okay, and as we continue with this case, it's still my X value is going up by 1, but take a look at my Y value. My Y value is actually multiplied by 4. So in this case, what I'm going to look at is, as far as my equation is concerned, my initial value is when X is 0, which is 1 still, but now my B value is not 2 like in the previous one, but it's 4 because you're multiplying everything by 4. So this is what this would look like. Now, exponential growth. So here's some terminology you need to think about. Nuclear reactions. If anybody had chemistry in high school, I mean, a lot of different with electrons and orbitals and stuff. It's in the long lines of like nuclear reactions, like your atom bombs. Money. Everybody in here understands money. Hopefully, we are saving money, and as we're getting into our jobs, we can use money into our retirement. The more we put in over time, it's hopefully going to grow exponentially. Population. Any kind of population, whether it's in, talking about the world population, the United States, a state, counties, cities, whatever the case is, it can grow exponentially as well. Now, the last thing I want to talk about with exponential growth is bacteria. Now, bacteria, I want you all to think of milk. Most of us in here use milk. Prime example was, this has been years upon years ago, but I was looking at our refrigerator and I noticed a big jug of milk. And I noticed that there's some discoloration in it. There was some green and some blue, and I knew what it was going to smell like. If anybody's ever seen this, it's sour milk. But what happens, and I'm going to make this really brief, is milk. So if you go to Kroger, Walmart, wherever you get your milk at, usually if you see the data, say like April 1st, usually that means you have about 7 to 10 days to kind of use your milk. After that day, it just depends on, how long of your trip is to your house. If you've left the milk on the counter, if you keep on bringing the milk in and out of the refrigerator for cereal and just leave it. There's a lot of different factors that can shorten that length, but usually it's about 7 to 10 days. And then it turns sour because the bacteria is actually feeding off the milk. Now, as far as a graph is concerned right now, the graph is a curve that kind of goes, it's flat, and it hits, and it goes straight up. And the growth factor, we're going to get back to this here in a little bit, the growth factor in this case is A is going to be greater than 1. Now, right below this chart, this table, I have this the standard exponential growth. It's n of t equals IA raised to the t. I is always your initial value. And I believe I spelled initial value wrong, so please forgive me on that. Your A is your growth factor, so remember for your growth factor, there we go, initial. Your growth factor is always greater than 1. And T is time. Now, time can be anything. It can be years, it can be decades, centuries, it can be months, hours, seconds, minutes. I mean, there's a lot of different units that we can use for time. Now, an example that I'm going to use to demonstrate this growth is n of t equals 100 times 2 to the t power. Now, this is the same where you have, it's in the same standard form as I times a to the t power. So now what we can ask you is a couple of things. We can actually ask you what the initial value is. We can even ask you what the growth factor is. So let's think about this for a little bit. What is the initial value? That means what number is where the I is. Well, in this case, it's 100. So, I mean, I'm not telling you what this is. This means this could be like $100, 100 bacteria. The growth factor is always attached to the exponent. In this case, is the t, which is 2. So this means over a certain amount of time, this is going to double. So now, to kind of demonstrate this, what I'm going to do is I'm going to put this in and show you what happens when n of t is 0, 1, 2, and 3, and see what happens. Now, so that means what happens when t is 0. So we start off with 100. We're doubling it to the 0 power. Now, anything to the 0 power is 1. So that's 100 times 1, which is 100. Now, I'm going to put 1 in for t. So 100 times 2 to the first power, anything to the first power is itself, so it's 100 times 2, which is 200. Then I want to do the when n of 2. So that means I've got 100. 2, now it's squared. 2 squared gives me 4. 100 times 4, which is 400. And the very last one is 100 times 2 to the third. Now, that is not, and a common mistake is 2 to the third is 6. No, it's 2 to the third is 2 times 2 times 2, which in this case is 8. So 100 times 8 is 800. Now let's look at the pattern. The initial value is 100. That's n of 0. And what it does is it doubles. So 100 doubles to 200. 200 doubles to 400. 400 doubles to 800. So without doing any kind of calculations, n of 4, that means I'm just going to double 800. So I'm not asking you this, but I could. What is n of 4? Well, that would be 1600. Now, exponential decay, radioactive half-lives, and also depreciation. Now, one thing with depreciation, I want you to think about this. What depreciates? Well, one big thing is cars. And everybody who's bought a car, especially new right off the car lot, it really depreciates pretty fast after you drive it off the lot. Other things, think of recreational stuff like campers and boats. You know, they depreciate as well. Now, the depreciation also is opposite of growth. So what I mean by opposite is if I look at the curve on the graph, it starts off very at the top of the y-axis and it curves all the way down to the x-axis. It never crosses it though. Now the growth factor or the decay factor in this case is going to be between it's 0 and 1. So that means you're talking about decimals and fractions. So that gives you an idea of an exponential decay part of this. Now, I'm going to do a similar example to my exponential growth. This time, n of t equals 4 times 1/2 to the t. Now, if you put this in your calculator, make sure you put everything that's the growth factor or the decay factor in parentheses. Now, what is the initial value? What is the decay factor? Well, let's look at the initial value. It's a number that starts on the outside, which in this case is 4. Now, the decay factor is 1/2. That is the number. In this case, most of it's going to be in parentheses, but it's also attached to the exponent, which in this case is t. So now look at 1/2. 1/2 does fit that criteria. It's between 0 and 1. So this is a decay. Now I'm going to do the same when n of 0, n of 1, and n of 2, and n of 3. So when n is 0, or when t is 0, what I'm going to do is I'm going to say 4 to the 1/2 of 0. Well, remember, anything to the 0 power is 1. So this is like saying 4 times 1, which is 4. Now look at the 1. What is 4? And then 1/2 to the first. Remember, if you put this in your calculator, make sure you put the 1/2 in parentheses. So 1/2 to the first power is 1/2. So that's like saying 4 times 1/2. So 1/2 of 4 is 2. Now my next one is going to be 4 to the 1/2 squared. So that's like saying 4 times 1/2 times 1/2, which is 4 times 1/4, which gives me 1. And the last one, 4 to the 1/2 to the third power. And if you put this in your calculator, I'm going to kind of shorten this up a little bit. That's like 1/2 times 1/2 times 1/2. So basically that is saying 4, 1/2 times 1/2 times 1/2 is 1 to 1/8. So 4 times 1/8 is 0.5, or it's 1/2. Now notice with my answers, I start with 4, that's my initial value, and I cut it in half because that's my decay factor. So 1/2 of 4 is 2, then 1/2 of 2 is 1, 1/2 of 1 is that 0.5 or 1/2. That's how we need to look at this. Now, as I'm finishing up, you're going to be actually asked several questions on WebAssign. And one, what they're going to do is they're going to give you a growth factor. The f of 0, in this case, I'm going to say equals 3. Remember, that's going to be my initial value. That's what we're going to start with. So now what I'm going to do is I'm going to say, okay, what happens, and I'm going to write this in. You can pick any number you want. I'm going to say, find when f of 2. So that means what I need to do is my initial value is 3. What it's doing is the growth factor, and it's a growth factor because it's greater than 1. So I'm going to put 2.5, and then I'm going to raise it to that 2 is actually my t, so I'm going to square it like that. And if you do your math just like this, you should get 18.75. Now, so just the key to this is knowing what your initial value is, and that's whenever x is 0. In this case, f of 0 is your initial value, which is 3. That's what I start with. In parentheses is my growth factor, which I'm given 2.5. And then what I'm trying to find is f of 2, so that's what it replaces my t, so that's why I square it. Now, here's one that has always given my classes a little difficulty. Now, I'll give you an equation. It's f of y equals 100 times 1.5 to the y power. Now, I'm asking, what is the decay factor? Well, I want you to think about this. The initial equation is a yearly. So you need to think to yourself, okay, year to decade. I know that there are 10 years in a decade, so I know I'm going to have to multiply something by 10. So what I'm going to do is I'm going to actually, for my decade factor, I'm going to take my 1.5 and I'm going to raise it to 10 because there are 10 years in a decade. So then I get 57.67. Now make sure you do 1.5 raised to the 10 power. I don't know how many times I've seen students do 1.5 times 10. That's not it. Now I know I'm not asking you this, but what our new equation would look like would be f of d for decades equals, now I'm going to still start off with 100, but now my decade factor is 57.67 raised to the d for decades. Now decades, I want you to think about this. Now, if you put in 1 for decades, that means 10 years. So that means if I ask you something in 10 years, you could put in 10 in the original equation or put 1 in for the d. It just depends on how you want to approach this. Now, century. Go back to the original. How many years are there in a century? Well, there's 100. So what I'm going to do is I'm going to still do 1.5. Now I'm going to raise it to 100. Now this is going to be a big, large number, and you're going to probably get something like 4.07, and it's probably going to say something like e to the 17, or it may say something like 4.07 times 10 to the 17. That's what that means. It's very large, and I'm sure most of us would like to see this in our bank account. Now, lastly, it's going to ask you a monthly factor. How do we determine what the monthly factor is? Now, this is a little bit different because, you're not going to multiply it. You're not going to think of 10 or 100 or 1,000 or whatever. Think of monthly. We're going to go backwards. So when we go backwards, think of fractions, okay? So I'm still going to use my 1.5. But now, think about months. How many months are there in a year? Well, there's 12. But it's a fraction. So we're going to take 1 month out of the 12 and we're going to raise it. So in our calculators, do 1.5 with that year to raise it, and make sure it's in parentheses 1 to the 1/12. Do not put 1.5 raised to 1/12 without parentheses because some of our calculators are not going to accept that. So that means what comes out would be my monthly factor should be 1.03. Okay, now my final one now what it's going to do is it's going to ask you, it's going to give you a problem. In this case, it's 7 times 3 to the t power. Now, in this case, the 7 is my initial value, and it's saying it triples every 4 years. So all it's asking you, though, is the yearly growth factor. What is the yearly growth factor? So the 7 is our initial. So it's just giving us some extra information that we do not need for this problem. Now, it says a yearly. So I'm going to use my 3 Now, when it triples every 4 years, okay, think about the year. It's a 4-year span, so think about when we went from a year backwards to month. Same thing here. This is a 4-year span. So when it says a growth factor, that means there's 1 out of the 4 years. So if we put this in our calculator, you should get 1.32. Now, I'm not asking you this, but if it asks you what is the new equation, you would want to put in something like f of y equals, our initial is 7, but instead of tripling, it's going to be 1.32 raised to the t power. Or I'm sorry, the y power, because we're using yearly. So I do hope this helps. Please email me if you have any questions over this. And this will actually, our homework number 10. Now, hopefully tonight or in the morning, I will put section 4.2 in. So please hang in with me. This is all new, like I said. Just please don't stress out. We're all working together. So just please be looking out for some more lessons. Thank you very much.